Data processing is a process of taking the raw data that were collected and processing it to be used for data analysis. The data process can include various steps that are listed here, but we will talk mainly about data smoothing or filtering and calculation of time derivatives in this lecture. Raw data looks like rows and columns of data sampled during the data collection. The number of rows your data will have depends on both the sampling frequency and the duration of data collected. If the data were collected at 200 Hz for 2 seconds, we will have 200 times 2 equals 400 rows of data. This is because the data were collected 200 times each second for 2 seconds. The higher the sampling frequency and longer the data collection time, more rows of data we will have. There is an inverse relationship between the sampling frequency and the duration of each row of data. If the data were collected at 200 Hz, each row of data represents 1/200th or 0.005 seconds of data. The duration of each row of data can be calculated as the inverse of the sampling frequency. Therefore, the higher the sampling frequency, the shorter the duration or the length of each frame of data will be. Each column of the data contains different variables. The more variables you collect during the data collection, the more columns of data you will have. When collecting three-dimensional kinematic data, there will be 3 columns for each marker track during the data collection because we will have x, y, z coordinates of the marker in separate columns. This is the picture of the raw data that we collected in the lab. You can see the many rows and columns of data here. Most of the data that we use in this class are smoothed or filtered. Smoothing or filtering means to minimize the noise in the data. This step is especially important when we want to calculate velocity and acceleration from the position data. When calculating velocity, you will take the change in position of the marker and divide that by time, over here, or the duration of each frame. The problem here is that any data we collect include a little bit of noise. The noise can be introduced from the error in the camera system, deformation of soft tissue under the reflective markers, shaking of the marker as you hit the ground hard upon landing, and from other sources. When you calculate velocity from the position data that contains noise, the noise will become magnified and end up contaminating the velocity data. If you look at the last equation here, the velocity calculated from the raw data with noise included will be equal to the sum of the true velocity plus the noise divided by time. Even when the noise in the position data is relatively small, say 1 millimeter, the noise can become magnified as you divide this noise by the duration of the frame, which is very short. In the previous slide, we said that the duration of each frame of data when collected at 200 Hz will only be 0.005 seconds. If you divide the 1 millimeter error by 0.005 seconds, the noise that will be introduced in the velocity data will be 200 millimeters per second. Here I am showing you the velocity and acceleration data calculated from the unfiltered data on the left side and the velocity and acceleration data calculated from the filtered data on the right side. You can see that the figures on the left have many random spikes, while the figures on the right is relatively smooth. This is particularly true for the acceleration data compared to the velocity data. These spikes are caused by the noises in the position data that are magnified in the process of calculating velocity and acceleration. For this reason, the data that is used for assignments and activity in this class will be filtered before being provided to you. Filtering of the position data is important for the calculation of kinetic variables too, because calculation of kinetic variables require velocity and acceleration data.